Let's say we're given the f of x equal to k times x cubed on the interval from 0 to 4 is a probability density function. We want to find k. Pretty standard type of question. So to find k, we have to set up the integral over the entire interval so that it's equal to 1, because that's part of the definition of being a probability density function, is that the area under the curve is equal to 1. So we're going to do the integral from 0 to 4 of k times x cubed dx. We're going to set that equal to 1. Then we're going to solve for k. So pretty straightforward. We're going to get k times x to the 4th over 4 from 0 to 4 to 1. We're going to plug in and we're going to get k times 4 to the 4th over 4 minus 0 to the 4th over 4 equal to 1. So it looks like we're going to get that k times 4 cubed, or k times 64, equals 1. So k equals 1 over 64. Sometimes the numbers are worse, sometimes they're better, but usually it's not too terrible. So our probability density function is f of x equal to 1/64 times x cubed on the interval from 0 to 4. When you're talking about the PDF, you do need to specify the interval. If I said my function was just 1/64 times x cubed, and I didn't tell you what interval it was over, I wouldn't really be specifying that it was a probability density function, because we need that interval so that we know that the area under the curve adds up to 1. Let's go ahead and find the other things for it. Let's go ahead and find the mean or expected value. These are, these are probably things your teacher will expect you to memorize, right? The expected value formula is not terrible. You're just doing the integral again, but now you're multiplying the whole thing by x. So it's going to be x times your PDF 1/64 times x cubed. Usually the numbers start to get pretty messy with these things. I would say simplify minimally. I'm going to bring out the 1/64. And I'm going to multiply x times x cubed to get x to the 4th. And we're going to integrate. We're going to get 1/64 times x to the 5th over 5 from 0 to 4. And this is where it's probably worth observing that 64 is 4 cubed. So this is going to be 1 over 4 cubed times 4 to the 5th over 5. That makes it pretty easy to simplify. Oh, 4 to the 5th over 4 cubed is just 4 squared. That's going to be 4 squared over 5, or 16/5. Not too bad, although this number, not too hard to find, but it makes the next calculation of variance kind of gross if we use the original formula. So let's look at variance. I'm going to remind you of the fact that there are 2 formulas for variance. So the variance of x, the kind of normal first way of seeing the variance is writing it as the integral from, I'm going to write the general formula just so everyone remembers it. It's the integral from a to b of x minus your mean squared times your probability density function. And then the alternative formula, the nicer formula, is it's the integral from a to b of x squared times your probability density function minus the mean squared, or the expected value squared. Either way is fine, but I will tell you this second calculation is almost always easier to do. So let's take a look at that. So for this particular problem, we're going to be calculating the variance as the integral from 0 to 4. And I'm going to use this formula here. So it's going to be x squared times 1/64 x cubed dx minus my mean squared. Again, not beautiful, but perfectly fine. Bring out the 1/64. I'm going to integrate x squared times x cubed as x to the 5th. And we're going to get, let's see, 1/64 The integral of x to the fifth is x to the sixth over 6 from 0 to 4 minus 16 over 5 squared. We could probably multiply that out. 16 squared is 256. 5 squared is 25. And then plugging this in, we're going to get 1 over 4 cubed times 4 to the sixth over 6 minus 256 over 25. And 4 to the sixth over 4 cubed is just going to be 4 cubed. So it's going to be 64 over 6 minus 256 over 25. And I feel like I've done more work than I really should have. I would leave it there, or probably even stopped sooner, right? The point of this exercise mostly is just to see that we can do it, not to actually simplify this number anymore. And then, of course, if we have the variance, the standard deviation is almost a freebie. The standard deviation is just the square root of the variance. So that's going to be the square root of this terrible number up here, 64/6 minus 256 over 25. This number up here, so I should point out, this number up here is pretty small, right? Which is not atypical. 64/6 is just a little bigger than 10. 256/25 is also just a little bit bigger than 10. This one is a little bit more bigger than 10 than this one is. So the difference is positive, which it should be. The variance should always be positive, but it's worth noting, oh yeah, this is actually pretty small. If you really wanted to, okay, this is right, 10 plus 4/6, right? 64/6 is 10 plus 4/6, and 256/25 is 10 and 6/25. And then you could cancel the 10s and just say, oh, this is 4/6 minus 6/25. So you wanted to make it look a little bit nicer, but not important. I noticed something, so I was like, oh yeah. But a pretty small number, right? 2/3 minus 6/25 is pretty small. Oh yeah, let's look at one more thing. So typically, if I were asking a question on an exam about a probability density function, I would probably ask all these questions. I would say, find the k value, if I'm going to do it that way, find the expected value, find the variance, find standard deviation, and then also find the median. So yeah. So we want to find the median. This is a reminder, our function, which is 1/64 x cubed, looks vaguely like this on 0 to 4. Has the usual cubic shape. If I plug in 4, I'm going to get, oh, interesting. Yeah. So I'm looking at all the area under that curve there, and I'm trying to find the place where half the area is on the right and half the area is on the left. So half the area should be here and half the area should be here. You can either set this up as the integral from 0 to m of your PDF equals 1/2, or you can set it up as the integral from m to, in this case, 4 of your PDF equals 1/2. And the idea here is really just use whichever one seems like it's going to have the easier limit of integration. In this case, I would definitely pick the first one because plugging in 0 is going to typically be easier than plugging in 4. So let's use this one. So, all right, I'm going to integrate this. I'm going to get 1/64 times x to the 4th over 4 from 0 to m equal to 1/2. I'm going to notice that 64 times 4 is just 4 to the 4th. So I'm going to say that x to the 4th over 4 to the 4th equals, from 0 to m equals 1/2. And then plugging in m, I'm getting m to the 4th over 4 to the 4th equals 1/2. So m to the 4th equals 4 to the 4th divided by 2. And so m is equal to the 4th root of 4 to the 4th over 2. Or if you prefer, m is equal to 4 over the 4th root of 2. Which, just for the sake of seeing where it lies on the, how does my calculator keep disappearing? Hiding myself in the wrong pocket. So let's see, the 4th root, so 4 divided by the the fourth root of 2. That's approximately 3.36. So this median, which is about 3.36, right, is much, right, it's way to the right. So we're saying, you know, half the area is on the right of that and half the area is on the left. So it's really, really close to the end. Very different than our average, right? Our average, just as a reminder, our expected value was, I guess it's not that different, was, I think it was 16/5. Yeah, which is 3.2, but different, right? So I guess they're not that different here, but they are different, which is important to be aware of. Let's see. Any questions about any of this so far? I mean, they're pretty straightforward calculations. They just can be messy. Yeah, let's see. Let's look at this. They all seem, I mean, they're all just, I guess the last thing we could ask, or the last type thing we could ask is, what's the probability that X is between 1 and 3? Or written more, you typically find the probability that 1 is less than X is less than 3. And I should mention, it doesn't matter if I say strictly less than, or if I make one of them and less than or equal to, right? It doesn't matter if you're including the endpoint or not. That doesn't change the probability at all. So this would just be the integral from 1 to 3 of our PDF. So then you would do the usual thing. You would integrate, you would get X to the 4th over 4 times 64 is 4 to the 4th. Or 256 if you prefer, from 1 to 3. So I plug in 3, I get 3 to the 4th over 4 to the 4th. I plug in 1, I get 1 over 4 to the 4th. I end up with 81 minus 1, so 80 over 4 to the 4th. And sure, you could reduce that fraction. That's a coincidence. I happen to pick an interval where the area under the curve happened to equal what our mean was. Totally a coincidence, though. Oh, 16/5. Yeah, right. Not a coincidence. Coincidence that it's the reciprocal of it. How about that? That's a coincidence. Less meaningful. Okay, so the other thing we can look at, or that we're going to look at, is there are some special functions that have very kind of well-known means and variances and standard deviations. So there are 3 specifically that we're going to look at. So let's look at this first one. The lifetime measured in years of a battery is an exponential probability density function. And it's given by f of t is equal to 1/3 e to the negative 1/3 t on the interval from 0 to infinity. Right, theoretically, there's no limit to how long the battery could last. Now, realistically, it's going to die at some point, but some batteries outlive other batteries, right? It's not always going to be exactly the same. The thing to notice, the thing that you should kind of take care to be aware of when you're thinking, is this an exponential PDF, is the coefficient out in front of E and the coefficient of T in the exponent should be the same but opposite. So this being a 1/3 and this being a negative 1/3 is telling me, oh, this looks familiar. This is what it should look like. So here's what our PDF kind of looks like. I plug in 0, I get 1/3. And it has this sort of shape. So first, let's just find some probabilities. So find the probability that the battery lasts less than 2 years. So I guess this is 2. Well, what we're looking at there is we're looking at essentially we want to find out how much area is under the curve to the left of 2, right? If we want the time it lasts to be less than 2, we want to find that area there. Okay, not too bad. We're going to do the integral from 0, probability that t is less than 2 is the integral from 0 to 2 of this function, 1/3 e to the negative 1/3 t dt. And the integral of this is not bad at all, right? We could do the u sub if you really wanted to, right? Letting u equal negative 1/3 t. Your du is negative 1/3 dt. And look, I essentially have that almost perfectly. Negative du is equal to positive 1/3 dt. So I could rewrite this integral as the integral of 1/3 dt becomes negative du, and e to the negative 1/3 t is going to be e to the u. And the integral of that's just going to be negative e to the u, which is negative e to the negative 1/3 t. So the integral of this is going to be negative e to the negative 1/3 t from 0 to 2, which is going to end up equaling negative e to the negative 2/3 minus negative, so plus e to the 0, or if you prefer, 1 minus e to the negative 2/3, which is approximately 0.487. So there's a 48.7% chance that this battery will die before 2 years has gone by. Okay. Now for the follow-up question that's actually what we want. What's the probability that the battery lasts more than 2 years? Well, the answer is kind of staring us right in the face. We could draw it again. Okay, here's our curve. And just kind of line it up. So instead of finding this area over here to the left, now I'm going to find this area here to the right. This is the probability that t is greater than or equal to 2. Whereas this here, what we've done before, is the probability that t is less than 2. Well, only one of these two things can happen. Either the battery lasts more than 2 years or the battery lasts less than 2 years. So if one of those things has to happen, and we already know the probability of the battery lasting less than 2 years is 0.487, then the probability of the battery lasts more than 2 years should be the remaining probability out of 100%. So we should say that the probability the battery lasts greater than or equal to 2 years is going to be exactly, I'm going to write a lot of things here, but it's really just going to be 1 minus this. Well, let's write it out. It's going to be the integral from 2 to infinity of 1/3 e to the negative 1/3 t dt. I would really rather not do an improper integral if I don't have to. So instead of doing the improper integral here, let's say instead this is going to be the same as 1 minus the probability that t is less than 2, which is going to equal 1 minus the integral from 0 to 2 of 1/3 e to the negative 1/3 t, which we just did. And that's going to end up equaling, that previous one was 1 minus e to the negative 2/3. So 1 minus e to the negative 2/3 is going to be positive e to the negative 2/3, which is approximately, 0.513. So basically, we're using the fact that all the area under the curve has to add up to 1. So if you're trying to find all the area to the right, it's usually easier to say, well, let's find the area to the left and then subtract it from 1. It's usually the way I would do that. I would do that. Not would do that. Okay. So then we want to ask other questions like, well, first of all, it's probably worth verifying. We probably could have done this first. Let's verify that it actually is a probability density function. Okay, so here's our function. (1/3 to the negative 1/3 t) on the interval from 0 to infinity. And technically, if someone asks you to do this, there are two things you should check. The first thing you should check is my function non-negative on the interval? And the answer here is yes. That function is definitely always greater than, it's actually always greater than 0, not even greater than or equal to 0. So yes, for sure. The second thing, which is the thing more people are usually concerned with, is showing that the integral from 0 to infinity of your function should equal 1. Oh well. So that integral, we did the integral before, but now we're going to use a limit. So it's going to be the limit as b goes to infinity of the integral from 0 to b of 1/3 e to the negative 1/3 t dt. That integrates as, well, we've already done before. The integral of 1/3 e to the negative 1/3 t is just negative e to the negative 1/3 t from 0 to b. Then we plug in b. And we plug in 0. We get the limit as b goes to infinity of negative e to the negative 1/3 b minus negative e to the negative 1/3 times 0. This part here, e to the negative 1/3 b, if b is going to infinity, we're getting e to the negative infinity, which is going to 0. Minus minus, e to the 0 is 1. So the area under the curve is 1, as we would expect it to be, right? That is what should be true if someone's telling you have a PDF. Okay, let's answer the other types of questions. And now here's where things are going to get a little bit interesting. Let's find the median battery life. And just to remind you what median means, the median battery life means half of the batteries will live less than this long, half the batteries will live longer than this long, different than the average. So you could either do it as, let's draw this picture again. So the median, once again, is where half the area is here, half the area is over here. So I could either do the integral from 0 to m of my PDF equal to 1/2, or I could do the integral from m to infinity equal to 1/2. I wonder which one I'm going to do, right? We're going to do the easier one. Always do the easier one. So again, we've integrated this a couple times now. The integral of this is going to be just negative e to the negative 1/3 t from 0 to m equal to 1/2. So then we plug in, we get negative e to the negative 1/3 m minus negative e to the 0 equal to 1/2. Let's simplify this a bit. I'm going to have, that's a positive 1, so I have 1 minus e to the negative 1/3 m equal to 1/2. Excuse me. That's a minus, that's an equals. Let's subtract 1/2 from both sides and add e to the negative 1/3 m to both sides. Then we're going to take the natural log of both sides. So we have the natural log of 1/2 equal to just negative 1/3 m. And then we're going to multiply both sides by negative 3. So m is equal to negative 3 times the natural log of 1/2. Or to make this look just slightly nicer, I'm gonna bring that negative up as the power here. So this is equal to positive 3 times natural log of 1/2 to the negative 1, which is just 3 times the natural log of 2, which is approximately 2.07 years. So half of the batteries will live less than 2.07 years, and half the batteries will live longer than 2.07 years. Okay, let's compare this to the expected average battery life. And this is where this part here, specifically the expected value and the variance, are going to be things that we're going to make comments about a little bit later on, because if you have a special probability density function like this one, there's a very, very fast way of just knowing what the mean and the variance are. So for this function, the expected or average battery life, it's the same calculation as it always is. It's the integral over your interval of x times your PDF. I should use, I've been using x inappropriately. No, I've been using t. Okay, I should be using t, not x here. That should be a t times your f of t. So in this case, it's going to be the integral from 0 to infinity of t times 1/3 e to the negative 1/3 t dt. Which I'm not super excited about, because one, I'm going to have to do integration by parts, and two, I'm going to have to do an improper integral. Let's do the integration by parts part first, meaning let's just find the integral without worrying about the 0 to the infinity part of t times 1/3 e to the negative 1/3 t dt. So I'm going to let u equal t, and I might as well let dv be the entire thing, including the 1/3 there, just because we've already integrated that like 4 times. We know what it is. So let's say that dv is 1/3 e to the negative 1/3 t dt. Our du is 1 dt, and our v is negative e to the negative 1/3 t. So then the integral of this is going to equal u times v, so t times negative e to the negative 1/3 t, minus the integral of v du, which is negative e to the negative 1/3 t dt. Simplifying this a tiny bit, I'm going to get negative t over e to the positive 1/3 t. Minus and minus is plus the integral of e to the negative 1/3 t. And that's going to be negative t over e to the 1/3 t. Minus, so the integral of e to the negative 1/3 t is e to the negative 1/3 t divided by negative 1/3, or times positive 3, times negative 3. We can check that if we want, but right, if we take the derivative of that, we're going to get negative 3 times e to the negative 1/3 t times the negative 1/3, which will cancel out the negative 3. And I would probably make the choice to do some simplification here. I'm going to write this as negative t over e to the 1/3 t minus 3 over e to the 1/3 t, and then actually factor out the over e to the 1/3 t. So this is really just negative t minus 3 over e to the 1/3 t. There is a good reason for this. I'm not just doing it because it looks super fun. So now let's find the integral. So the integral from 0 to infinity of t times 1/3 e to the negative 1/3 t is going to equal the limit as b goes to infinity of, we already know what the integral of this is. It's that right there. So it's the limit of that integral, negative t minus 3 over e to the 1/3 t, evaluated from 0 to b. Okay. And then we're going to plug in b. The limit as b goes to infinity of negative b minus 3 over e to the 1/3 b, minus we plug in 0, and we get negative 0 minus 3 over e to the 0. Okay, now question. as b goes to infinity, what happens to this fraction here? Well, the top is going to negative infinity and the bottom is going to positive infinity. We have an infinity over infinity type. There are two ways to address this. One way, which I don't really want to do, is to use L'Hopital's rule, which I don't know. Did you learn L'Hopital's rule in 16A or 16B? Okay, probably. Often it gets skipped. The more typical way people kind of address this, they're like, well, e to the 1/3 b is an exponential function. As such, it grows exponentially fast, whereas just b on its own is a linear function. This exponential function is going to be a much, much larger thing than this linear function. So I have something that's getting bigger, but something that's really getting bigger. This fraction is going to get smaller and smaller and smaller. So I'm seeing this as a tiny infinity over a much larger infinity. And that's going to go to 0. Plus 3. So the average battery life is 3 years. Okay, let's find the variance, and then we'll talk about, well, yeah, in fact, I'm not even going to do the work to find the variance because it's kind of gross. But let me show you. So let me show you. So if I want to find the variance of the battery life, well, again, using the nicer formula for variance, that's going to be the integral from 0 to infinity of x. Sorry, I keep wanting to write x instead of t. The integral from 0 to infinity of t squared times f of t, which is 1/3 e to the negative 1/3 t, minus the mean squared. Now, doing this integral is also terrible, right? You have to do integration by parts twice, which I guess we could. No, I really don't want to do it. Like, I can do it if you want me to do it. Do you want me to do it? No, okay. I didn't think you wanted me to do it. So if you do integration by parts twice, you end up getting, the integral ends up equaling 18 minus this 9 over here. So you get 9. So the variance here is 9. And then the standard deviation is the square root of 9, which is 3. So the mean is 3 years and the standard deviation is also 3 years. This is not a coincidence. So here's what I want to point out. For a PDF of the form, let's write it this way, f of x equal to 1 over a times e to the negative 1 over a times x, the mean is a, or we'll call that the expected value, and the standard deviation is also a. And that is always the case. So if we go back to the original thing, be like, okay, our PDF is 1/3 e to the negative 1/3 t on 0 to infinity. Great. We know that the mean is 3 and the standard deviation is 3 right off the bat. And then we can also say that the standard deviation is 3, then we know that the variance is 3 squared, which is 9. I should say, and so I was a little careless here. I said for a PDF of the form this, I forgot to write the interval, which is kind of vital. It is on 0 to infinity like that. This is always the case. The mean and the standard deviation are always both equal to the a value there, which is kind of nice. So for example, if you're given a PDF, say f of x equal to 1/7 e to the negative 1/7 x on the interval from 0 to infinity, I know right off the bat, great, my expected value, or my mean, if you want to call it that, is 7, and my standard deviation is also 7, and my variance is 49. So not too terrible. The only thing you have to be careful about is making sure you have the right thing. So it's often easy to make a mistake. Be like, okay, so let's say I was given, let's say my, one more example, let's say my probability density function for the lifetime of a battery, no, let's make it, of a cheaper battery is f of t equal to 5e to the negative 5x, again on the interval from 0 to infinity. So what's the expected lifetime of this battery? It does work. It's not 5. It's 1/5, right? It's always the reciprocal of whatever number's out here. So just like in the previous one, in the previous ones, we didn't really see it that way, but right, really the expected value is the reciprocal of 1/7. Or the expected value here was the reciprocal of 1/a. Here, right, I could write it in a silly way. I could write this as, of course I used an x when I meant to use a t. I could write f of t as 1/1/5 times e to the negative 1/1/5 t, but there's no need to do that, right? We can see it's just going to be whatever the reciprocal value is going to be. So be careful about that because it's easy to get kind of turned around as to what should be what. So here, the expected lifetime of the battery would be 1/5 of a year. And the standard deviation for the lifetime of a battery would also be 1/5 of a year. The variance would be 1/25. The variance isn't measured in the same units though. So that's why that's really one of the reasons we actually talk about standard deviation instead of variance, is because the standard deviation and the thing you're measuring are measured in the same units, whereas the variance is the square of those units, which doesn't always really make sense, right? It doesn't make sense to talk about years squared, right? That seems like a weird thing to be talking about. Okay. So most of the time, when people are asking you questions about things that have probability density functions, that are these exponential functions like this, their intention behind those problems is for you not to do these terrible integrals that are improper, but to just know, oh, I know how to find this because it's a formula. It's not super satisfying, but it is the truth. There are two other special probability density functions, which we're going to talk about. So let's look at this next one. The wait time in minutes at the checkout line oops, sorry, I got yeah, is sorry, is uniformly distributed so these words I feel like always throw people off. People hear uniformly distributed and they think bell-shaped curve often, which is not correct. Someone says it's if someone's talking bell-shaped curve, there's a different word to use that. We say it's normally distributed. So normally distributed means bell-shaped, also known as a Gaussian curve, whereas uniformly means completely horizontal. So and I forgot an important word. The wait time in minutes at the checkout line is uniformly distributed. Sorry. Over a 10-minute interval. So here's what this looks like. Our function f of t is 1/10, and the interval is from 0 to 10. Graphically, it is not exciting. It looks like this. There's my really, really exciting function. That is a PDF because the area under it, right, that area is equal to 1. So, what's the probability that we wait less than 3 minutes? Okay, so we're going to do the integral from 0 to 3, because that's less than 3 minutes, is anywhere from 0 minutes to 3 minutes, of my function, 1/10. See, the nice thing about this uniform distribution is it's very easy to anti-differentiate. That's just going to be 1/10 times t from 0 to 3, which is going to end up being 3/10. You could also literally just look at the graph. Say, okay, well, I'm looking at this graph and I'm going from 0 to 3. Well, great. I know how to find the area of a rectangle. The area of that rectangle is base times height, which is 3/10. So for uniform distribution, really the answer to any probability question is just take the length of your interval. In this case, the length of my interval was 3, and multiply it by the height of the function to get the probability. It really couldn't be much more straightforward. So let's look at 2 other things. How long do we expect to wait? What's the expected value of how long we're going to wait? Well, let's think about it this way. I guess my question is, if we are uniformly distributed, where the least amount of time we could wait is 0 minutes and the most amount of time we could wait is 10 minutes, what do we think the average of that might be? If you had to guess a number, what would you guess? Yeah. Right. I might guess 5. 5 seems like a pretty good guess. Let's check and see. So the expected value is going to be, again, and you definitely should memorize this particular formula. Stop trying to do things. I'm not talking to you. Okay. So the integral from, so I should say the integral over your entire interval of your variable times your PDF. Right, that's how we calculate the expected value. In this case, that's going to be the integral from 0 to 10 of t times 1/10 dt. Integrating that, we're going to get t squared over 2 times 1/10 from 0 to 10. Plug in 10, I get 10 squared over 2 times 10 is 20, minus 0 squared over 2 times 10. That's going to equal 100 over 20, which is, of course, 5. That's also notably here the mean or expected value is the same as the median. Because the median, which would cut this graph in half, is exactly the same at 5, right? If we go to 5, half the area is definitely on the left, half the area is definitely on the right. There's certainly symmetry here in that way. So the median is also 5. Median is equal to the mean, which is equal to 5 in this particular case. And that's always true for a uniform distribution or just a perfectly flat distribution. The mean and the median are always going to be the same. Let's do the variance as well. I think the variance is worthwhile. So I want to find the variance. Again, I'm going to use the quote unquote easier variance formula. It's going to be the integral from 0 to 10 of t squared times f of t dt minus your average squared. So that's going to end up equaling the integral from 0 to 10 of t squared times 1/10 dt minus 25. And then we're going to integrate. We're going to get t cubed over 10 from 0 to 10 minus 25. T cubed over 10 is 1,000 divided by 10, which is 100. So we're going to get 100 minus 25, which is 75. Yeah, I don't remember the actual. I know there's a formula for this one, but I actually don't remember what it is. So these ones, okay, question. Oh, yeah. Yes, thank you. There's a 3 there that I forgot. So really, we should be getting 100 over 3 minus 25. So that actually is going to change this up a little bit. That's going to end up being 100 minus 75 all over 3. So we're going to get 25 over 3. Now let me double check that because I feel like I could be t cubed over 3, t cubed over 3 times 10, 10 cubed over 10, 100 over 3. That looks right. Okay. So you can memorize the formulas for these as well. More generally, I would say that for a uniform distribution, the standard, so for f of t equal to, now here's actually something kind of worth knowing. For your uniform distribution, your function is 1 over b minus a on the interval from a to b. Right? It has to be like that. If you're going from a to b, the function height has to be 1 over a minus b. B minus a, sorry. Otherwise, the area won't be 1. Area here is equal to 1. The average or the mean is always just the literal average of b and a. It is a plus b divided by 2. Just like the previous one, 10 plus 0 divided by 2 is 5. And then, honestly, I don't remember what the formula is for the other one. So let's find it. So the variance is going to be the integral from a to b of your variable squared times your probability density function, which is just a constant, minus the mean squared. It's probably easier just to calculate it every time instead of memorizing this dumb formula. But we can find it. So we're going to get t cubed over 3 times 1 over b minus a from a to b minus a plus b squared over 2. So plugging in b and a, we're going to get b cubed minus a cubed over 3 times b minus a plus b squared over 2. And I'm sure this simplifies in some nice way. I think it ends up being like b minus a cubed over 12 or something. I don't actually know because I don't remember it and it's not in my notes here. This factors cancel the b minus a. And then we have a squared plus 2ab plus b squared over 2. And then we get a common denominator. So multiply this by 2 over 2. We get 2b squared plus 2ab plus 2a squared over 6. Multiply this by 3 over 3. We get 3a squared plus 6ab plus 3b squared. And then if we subtract them, 2a squared minus 3a squared is negative a squared. 2ab minus 6ab is negative. I'm worried now. I feel like I made a giant mistake somewhere. Mm-hmm. Yeah. Which then means I should have multiplied this by 4/4 and this by 3/3. Ugh. Thanks, good catch. I was really about to give it like a little crazy there. So that's going to end up being, so if I multiply this by 3/3, I still get that, except now the denominator is 12. And if I multiply this by 4/4, my denominator is going to be 12. My numerator is going to be 4b squared plus 4ab plus 4a squared. I love how I turn my 2's into 4's. So then we get 4b squared minus 3b squared, which is 1b squared, 4ab minus 6ab, which is minus 2ab, and 4a squared minus 3a squared, which is plus a squared over 12. And then that ends up being b minus a quantity squared over 12, which is what the formula is. I wasn't sure if it was cubed or squared, but yeah. So you can memorize that if you really want to. I clearly can't because I couldn't remember it, but it's usually just easier to directly compute the mean and the variance of a uniform distribution if you have to compute it, as opposed to memorizing formula. Whereas with the exponential distribution, it is much, much easier just to memorize that the mean and the standard deviation are both the same value, which is the reciprocal of that coefficient. One more special type of function, the standard normal probability density function, which if you've ever taken a statistics class, you have seen before. So here is the very general way of writing it. F of x is equal to 1 over sigma times the square root of 2 pi times e to the negative x minus mu squared over 2 sigma squared on the interval from negative infinity to infinity. I will point out that this function actually cannot be integrated. So this function, so I should observe a few things here, right? So in this formula here, mu is the mean. And sigma is the standard deviation. If you've taken a stats class, then you might know that when you're looking at like a standard normal Z table, we typically are thinking about or letting the mean be 0 and the standard deviation equal 1. And when that's the case, our probability density function looks like 1 over the square root of 2 pi times e to the negative x squared over 2. Which just looks a little bit less complicated. It's still fairly complicated, but I really want to have to stress is this function cannot be integrated. We are not just we, right? It's not just like we don't have the tools in this class. It is literally a function that does not have a nice antiderivative. That doesn't stop us though. That's why there's a whole table of z scores with the areas under the curve, because instead it's kind of like back before we had calculators, like people had trig tables and they had all these different trigonometric values for different angles, right? Because they wanted to know like these were important functions and we want to know what they were equal to at certain values. Same idea here. This is an important function. We want to know how much area is under it at different places. So we have this whole table that tells us all these different values of this function. So a couple things to say about this. This function has this shape. So generally, f of x equal to 1 over sigma squared root of 2 pi e to the negative x minus mu squared over 2 sigma squared has a bell shape. It looks like this. The mean is always the highest point. So the highest point occurs at the mean, and then one standard deviation is about that far. And you can't really do a whole lot with this. But so the types of questions we can ask with this are the following. So let's say I gave you this. Let's say f of x is the probability density function 1 over 11 times the square root of 2 pi times e to the negative x minus 100 squared over 242. Let's find the mean, the variance, and the standard deviation. And the whole point is just that you're supposed to be like, well, I've seen this one. Oh, sorry, this is on. The whole point here is like, well, okay, I can identify the mean by knowing the mean is essentially the thing that is getting subtracted from x. So looking at this whole thing, I can see, oh, look, there's the mean right there. The mean is 100. The standard deviation is the thing in this fraction out here that's multiplying the square root of 2 pi. So the standard deviation is definitely going to be 11. And then because variance works the way it does, the variance is of course going to be 11 squared, which is 242, which is 121.